This discussion is about implementing a sparse or CSR matrix multinomial distribution for Naïve Bayes in Python. Sort of an interesting topic. My name is Olin Hartin. I'm a professor of practice at Arizona State University in the electrical engineering department. And so let's talk about the motivation for this discussion. Naïve Bayes is used in natural language processing. One of the interesting areas of natural language processing is sentiment analysis. The idea of sentiment analysis is to build a model that can take a statement and determine whether it was a positive statement or a negative statement. And basically what you do is you train it. So for instance, we would start by training it using a series of positive and negative statements. For instance, this burger tastes good is a positive statement, and I tell it that that's a positive statement. And I hate my boss is a negative statement, and I tell it that's a negative statement. And then when I give it, if I use a large data set that has a lot of positive and negative statements, which are identified, I can create a model in sentiment analysis using this data set of known sentiments, train a model, and then we can use that to interpret the sentiments of new documents where we don't know the sentiment. This is very useful in a number of different areas. We're going to use it for movie reviews, but a common area to use this would be stock market predictions, where you download a lot of information in the media about companies, stocks, and the economy, and you classify the statements and determine whether they're positive statements about something or negative statements about something. Now, one of the nice things about this is there are a couple of different machine learning algorithms that are commonly used as benchmarks. They're not necessarily the best ways to do sentiment analysis, but they're commonly used as benchmarks when you're discussing other methods. And two of those sort of standard basic methods are logistic regression and Naïve Bayes. And logistic regression is a little more accurate. And Naïve Bayes is generally a lot faster, but not always. So let's say we're going to do a bunch of movie reviews, and I'm going to use a data set. I'll give you the data set reference in a moment. But let's say we're going to do a movie reviews, and some of the reviews are positive, some of them are negative about different movies. We have a data set that's set up where it has been pre-identified that this was a positive statement and this is a negative statement, and so on. And we're going to use this to train a model that we could then use on future movie reviews to determine general positive and negative reviews on movies. Keeps someone from having to read a lot of reviews. All right, so let's imagine now that we have a lot of movie reviews, and each review is an observation, right? So this is the number of movie reviews. And now, let's say we want to keep track of how much time it took to train the model. And so we increase the number of movie reviews that we use up to about 50,000 right here, about 50,000. Now, for up to about a little less than 1,000 here, we compared logistic regression, that's in blue, and Naïve Bayes, that's in this sort of mustardy color. And we see up to about a little less than 1,000, Naïve Bayes is pretty competitive with logistic regression in terms of time, about the same amount of time. But then after a certain number of reviews, perhaps around 1,000, Naïve Bayes is much faster, right? Because this is how long it took to do the fit. And this is a log scale, so this is a lot faster. Now, these are n log n type problems. And logistic regression, if I do a fit to this curve, the blue curve, I get 0.002 times n, the number of movie reviews, times log n in seconds. And that's this trend curve fit to this. But if I use Naïve Bayes, and let's say we'd use this portion of the curve, it's 0.002. So it's a lot faster. This is a lot faster than logistic regression as the plot indicates. What about accuracy? Well, up to about maybe a few hundred movie reviews, they have similar accuracy. Maybe Naïve Bayes does a little better in this case for a smaller data set. But then for large data sets, eventually you see Naïve Bayes is not quite as good as logistic regression, but it's very good. Still very good. It's very comparable to logistic regression. It does almost as well, but we know it's much faster. Now, what we did in this is we split our data set. If this is our data set here, I think of it as a pie, we took 2/3 of the pie and used that for training, and then we used a third of the data set to test how good the resulting model was. And this is a plot of the performance of this test data set, or validation. Validation. This is a common method. And there are more sophisticated methods, but this is generally good enough for this discussion. Now, well, we're going to describe a method of using this using Sklearn tools, and these are learning tools. These are as a free library that's available. And using this free library, we run into a problem. For about 50,000 movie reviews, we can see that we're using about 2.9 gigabytes of memory when we use logistic regression. But when we use this large data set of movie reviews, right, Naïve Bayes requires a large matrix, a large amount of memory. And suddenly we see there's a barrier to using Naïve Bayes for large problems. And we'll talk about what this problem is, and then we're going to talk about a solution. Okay, now let's do a little bit of background on the methodology. To do some sentiment analysis and logistic regression, what we want to do is we want to take every word in the review. Let's say I like Clint Eastwood. And we're going to take every word in this, and you want to determine the relevancy of this word, and in order to make this prediction. Now remember that we're really interested in word relevancy because some words don't have any relevance. So for instance, if a word is used more in a document, it might be more relevant. If you use a word of multiple times in a document, it might be more relevant. It might be something you really want to pay attention to. But if it's in every document, then it starts to be more likely that it's a glue word. For instance, the most common word is probably in any document, any set of documents, is probably the word "the," and which contains no real meaning. Now remember, in sentiment analysis in natural language processing, grammar is not interpreted. It just takes the words, turns them into a number, and uses that to build a model to make a prediction. And so one of the things we want to do is we want to use some indicator of the word. When we turn this into a number, we want to use an indication of the word that interprets its word relevancy. Okay, so we're going to use TF-IDF. And so the first part of TF-IDF is term frequency. And this TF determines the frequency that word occurs in the document. And we want that to be as high as possible. But in order to eliminate the words that are in every document, we use the inverse term frequency. And we're going to multiply the term frequency times the inverse term frequency plus 1, and this will be our TF-IDF, our interpretation of document relevancy. And the way inverse term frequency works is it's the log of the number of times it occurs in a document divided by the number of times it recurs in every document, right? Number of documents containing it. So if it recurs in every document, it's less relevant. If it recurs in one document, it's more relevant. And so we have an example here. If is in if there are 3 is's in the document, then that would be 3 here. If it's in every document, then that would be a 3 here, and TF IDF would be 0. So we're going to multiply TF times IDF plus 1, and so it would just be the term frequency. So this is our way of determining word relevancy, and I think it's sort of an ad hoc or sort of a way that works method that was put together over time. Now, so what we're going to do is we're going to read in a data set, perhaps from a comma-separated value file. We're going to tokenize the word, determining the word relevancy. We're going to do a couple of things to do that. We're going to split the data into training and test data sets. Then we're going to use logistic regression and Naïve Bayes to build machine learning models, and then we're going to compare and validate the models based on the validation or the test data set. Now, very often when we train a model, the training prediction is almost perfect, right? And it's only when we apply a new data set to it that we see that there are problems. Okay, so let's talk about the method of building this word relevancy. First thing what I'm going to do is we're going to download a list of words in the English language called stop words that are glue words. These are words that wouldn't be useful in sentiment analysis because it doesn't use grammar and because some words don't have much imported value in determining sentiment. And we're going to use this little Python algorithm here to, use this little Python algorithm here. I'm going to call it the targetizer porters. And what we're going to do is we're going to do 2 things in this. One is I'm going to take our text, our document, and split it into a series of words. And then if that word is not in the stop words, I use it. If it's in the stop words that I've downloaded, then I don't use it. Second thing we're going to do is we're going to do a stemmer. Now the porter stemmer, what it does is, for instance, the word give and the word giving will have the same stem, and so it'll just use one word, give, for the 2 words. Now this is an advantage because it eliminates a lot of tenses and other things that are not used in sentiment analysis. So here is our algorithm that determines TF IDF, and I'm going to pass everything through the tokenizer porter function that we built before we do it, and this will create a TF IDF. And here this builds the TF IDF object, and then we're going to transform our training data to a TF IDF format, and this will be that TF IDF data. Okay, so now we have word relevancy. We have a data set, X TF IDF, that contains word relevancy. Now, one of the problems is TF IDF builds, well, think of it as a matrix, and each column in a matrix is a word. We'll think of it as a feature, but a feature which is something that can be used for training. The columns of data, these would be observations or reviews, and these would be words. Now, not every word occurs in every document, so most of this matrix is 0, right? I mean 99% 0, because most words occur in a few documents, but they don't occur in every document. Take my example. Clint Eastwood maybe occurs in a few documents, but it doesn't occur in every document. So most of the values of this matrix are 0. Well, if we store it in this format, this is called a dense matrix format. We store it in this dense matrix format, then it's very wasteful because we're storing a bunch of zeros. Another way to do it that isn't so wasteful is the sparse matrix format. And you can think of this as, I just need to store this number and which row and column it was in. I just need to store this number in which row and column it was in. And for matrices that are very sparse, almost all 0, this is a much better way to store the matrix. And it turns out TF-IDF is returned from this algorithm in a sparse matrix format. The particular sparse matrix format that is used is something called CSR, or compressed sparse row format. Now, what happens whenever we use this in Sklearn is that we have to do a conversion to dense matrix format right here in order to use their Naïve Bayes algorithm. And here's the code where we say, well, we're going to take the TF-IDF data, take it to dense format, and then use it to do our fit of our model and our prediction, right? And the problem is this conversion to a dense format converts it to a large matrix, which is largely 0, a wasteful thing to do. So what we're going to do in this discussion is we're going to create our own version of this multinomial Naïve Bayes. We're going to create our own version that uses the sparse matrix directly. First, in order to do that, we need to talk about Naïve Bayes. Now, Naïve Bayes is a statistical method, and it allows you to make a prediction. Now, let's talk about this. Let's say I have a data set, and I made a measurement in the data set, and the probability of any particular data measurement is PD. Is the probability of a combination of different values would be measured together, right? Now, PC is the probability of each class, and we're going to classify this into classifications. In this case, for sentiment analysis, the two classifications are a positive sentiment and negative sentiment. So this would be the probability of a not positive and negative sentiment in the data set. Very easy to calculate. You just go through the data set and count the number of positive and negative sentiments and divide by the total number. So this is easy to calculate. Now, this is a posterior probability. This is the probability that you could make a particular measurement D, that's a series of a specific set of measurements, given that it's in class C. And Naïve Bayes, this Naïve Bayes algorithm, or this Bayesian statistics equation, tells me that I can calculate the probability that it is in class C given that I know what measurements were made using this equation. And this is useful. So if we make a series of measurement and we want to know what the probability is in a particular class, we could do this calculation. And that's the way we're going to do this. Now, this is the posterior probability that given a particular measurement, it's in class C. All right. Now, part of the problem is we can't really know in the probability of a particular measurement, and this is sort of complicated in most problems. It's what is the likelihood that this combination of feature values, these combination of measurements that are made, could occur together? It would be very difficult to determine that probability, and so we're just going to not do it. We're going to get rid of this and change the equation to this form. Now you see that the consequence of this is now we know the relative probability of each class, but we don't know the actual probability. Well, there's sort of a trick. If you know that it's one of the classes, you know that that everything has to be in one class or another. So you could sort of back out the actual probability later on. But it's enough to know the relative probability. All I'm really interested in is what's the relative probability that it's a positive sentiment and the relative probability that it's a negative sentiment. If one's greater than the other, I use that one. Then if it's more likely that it's a positive sentiment, then it's a positive sentiment. And that's all I need to know. I don't need to know the actual probability. So not knowing the probability of the data set's not a problem. And later on, we're going to make other assumptions that make that that require us to limit ourselves to a relative probability anyway. Now, if we think about it, this measurement PD is actually a series of measurements, right? D is, the concept of D is that it's the measurements that we made, but it's a list of measurements that we made for each feature. In the case of sentiment analysis, it's the word relevance for a series of words, some of which are going to be 0. So this is the word relevancy for each of a series of words. And so that's what D represents. All right. So in order to do this, we're going to need to be able to make this calculation. How are we going to calculate the probability of a series of measurements given that it is a particular classification? This is why Naïve Bayes is naive, is we're going to make an assumption in order to do this. And as in a lot of engineering and science problems, we make a series of assumptions until we get down to a problem we can do. Now, what we're going to make, the assumption that we're going to make is that all of these measurements, x1, x2, x3, so on to xn, that they're independent. That the likelihood of x2 being a particular value does not impact the likelihood of the value of x1. And this is in general not true. But let's talk about this. Now this would mean that if I take the column of all x1s for all of my data set and the column of all x2s for my data set, they'd be uncorrelated, right? And this is the correlation, the dot product or the correlation of, for column I and column J, they would be uncorrelated. Well, that's sort of just a complicated way of saying that I'm going to assume that they're unrelated and that I can determine the probability of each of them independently. Now, if I can do that, I can say the probability of this set of measurements is just the probability of each measurement given C, multiplied together. And this is a simplification. It implies that each measurement is independent. Interestingly, in the real world, each measurement is almost never independent. And you would think that this would cause Naïve Bayes to be an ineffective method, but in fact, it doesn't. In fact, Naïve Bayes is effective even when these measurements, as in most cases, are not truly independent. It's more effective if they are, but it's very effective even in cases where they are not independent. It's sort of an interesting aspect of this. Okay, so now all we need to do is be able to calculate the probability of each measurement given a particular classification. And well, for this data set, we're going to use something called the multinomial distribution. And this is a calculation of the multinomial distribution for Naïve Bayes. Now let's say that we have, here's our data set, right? And we have a bunch of different reviews. And for each review, we have a word, a series of words that may or may not be in the document, and a number here that was the relevancy of that word in that document, right? 0.2 maybe, okay? And so on. Now, if I think of each of these columns as a feature, this is feature 1, feature 2, feature 3, feature 4, right? If I think of each of these possible words as a feature, then the multinomial probability can be given by this calculation, where this is the probability that this feature occurs in this classification. So I take all of the cases here for feature 1 that are positive classification, and I take that to the power of x1, the word relevancy, for a particular measurement, and I can make this calculation. Now notice that this is multiplied by this upfront series of factorials, factorial of the number of observations divided by the factorial of each of these measurements, right? But this part right here is just an easily calculated probability of this feature existing, being non-zero, for each classification taken to the power of x1, which is its word relevancy, for each of the feature columns in our data set. Very easy to do. Well, this part here up front isn't easy to do. Let's talk about why. First, if I had 150 observations, that would be 150 factorial is 5.7 times 10 to the 262. Big number. Can't do that. And so we're just going to not do this up front. And the other problem is that we're going to use TF-IDF, which is a fraction for our word relevancy. And so we can't really take the factorial of a fraction. So we're just going to eliminate this upfront term. We're just going to eliminate it. Well, what this will do is this will give us a proportional a relative probability. But we were already working in relative probabilities anyway, so not a problem. All right, now, how do we calculate the probability of a feature given C? Well, for natural language processing, multinomial probability, we're going to use TF-IDF, as we described, as our word relevancy. And so the way you do this calculation is the posterior probability of feature F being measured given class C. That word occurred in this class, that is. We're going to sum up all of the TF-IDF values that are, let's say, positive sentiment in feature F, and all the ones that are negative sentiment. So this would be for, if we're going to do for the positive sentiment, you would use just the sum of all of the TF-IDFs in that feature that had a positive class. NC is the number of TF-IDF values for class C. Sum of all TF-IDF values in the database for class C. So this is beautifully easy to calculate. All right? Now, nothing in mathematics suggests this should not work for a sparse data set. To motivate this, consider the consequences of such an algorithm. All right, so this is the training time with this red curve here. That's this curve, right? Is the training time using the dense matrix conversion that we did earlier using Sklearn. And you see that it is a third order to the number of documents. In other words, the training time shoots way up when you get a large number of documents. And this is due to the large memory usage of this sparse data set. Now, if we could find a way to use this is due to the large memory usage of the dense data set. Now, if we could find a way to use a sparse data set directly, then we would get this. And it would be linear, the time would be linear with the number of movie reviews. And that would be great. This is a huge advantage for Naïve Bayes, which we said gave almost as good a result as logistic regression. But if you take the amount of time and the prediction, the quality of the prediction together, Naïve Bayes is quite a bargain. All right, so let's talk about our implementation in Python. Now, Python is a high-level language that simplifies the algorithm significantly. Now, you could make an argument against using a scripting or interpreted language, that it would be slow in a problem where you're interested in computational speed. The best argument for using an interpreted language is that we're manipulating data sets which are then passed on to compile libraries for computation. Also, high-level languages tend to simplify the programming task significantly. For problems where speed is needed, we can do a Python to do intermediate testing and then rewrite the code in C, or we could use something like Python, for instance, which will do a Python to C conversion where it can then be compiled and run much faster. Okay. Now, in any project, we have to determine the criterion for success. For our criterion for success is that our sparse version gives the same or perhaps better results than the Sklearn version of the multinomial that we have access to when we convert to a dense data set. So what we're going to do is we're going to compare our results of our algorithm, which uses a sparse data set, to the Sklearn version that doesn't, and just make sure we get the same results. Now let's use a publicly available data set. This is an IMDb movie database, and this is a link to that database. It has 50K movie reviews. For simplicity, we're going to use object-oriented programming, and what we're going to do is we're going to make our multinomial version have the same methods as the Sklearn library, so it'll be easy to test them and compare. To test our results, we're gonna compare them for a large number of observations or reviews. And I really sort of already showed you how that works because I showed you the plot of what happens when we did it. So this is what's going to happen. This is the comparison with the dense data set, and this is the comparison with the sparse data set with the same prediction performance. I'll do a demo at the end with a small data set just to show you that how it works. All right, so how does the CSR sparse matrix data set work? Well, it's a little complicated, but not terribly. First, there's an array called data, and it has the values of all. This would be a form of a dense matrix here, right? And you see here all of the non-zero values, A, B, C, D, so on, are here in the matrix, and they're just in this array. And there's a matrix or an array called indices that list the columns that they're in. So this is this first one is in A is in column 5. You see it's column 5 right here. And then there's another array that lists the rows that exist in each case. So this first one is in row 0, A is in row 0, and it's column 5. The second one is in row 1, and see this is B and C, this is in row 1 and 6. And so we see this is in column 1 and 6, but it's in row 1 here, and so on. And so with these three matrices, with these three vectors, we can interpret what the sparse matrix looks like without building it. All right, so let's build our multinomial object-oriented program. So first thing we're going to do is we're going to create a class, a multinomial class, and I added an S to it, so this is my version. This just looks just like the one that Sklearn made, except that it has an S here so that I can differentiate the two. And we have some data that we pull in, the number of features, the number of classes, and so on. Some useful data that we pull in and calculate the prior probability and so on. So these are matrices that we set up front in order to fill later on with our calculations. And we'll see how we fill those. First thing is we need to use this CSR format, and for any row, well, I'm going to call this is the row observation underscore P, the pth row number P. I'm going to take that row and I'm going to determine which columns and which data values are in that row. And that's going to come, I'm going to return that in list J. And then so F will be all of the features or columns that contain non-zero values in that row, and D would be those non-zero values. And I'm going to return the columns and the values. In fact, I actually scaled it by the maximum value of D. Now, how do we determine the multinomial? How do we determine this multinomial factor? Well, we remember this from the multinomial probability. We remember this from a previous slide. We said that for a particular word, given a classification C, we could calculate it in this way. And all we have to do is sum up the number of values, some TF IDF, for a given class in feature F. And that will give us let's say this was a positive sentiment and this is the first class. I would sum up all of the positive sentiments, the TF-IDFs with a positive sentiment in the first class. Alpha is a scaling factor, sort of a factor that smooths the result. And then we're going to divide by the NC, which is the number of all TF-IDF values in the database for class C, all the positive sentiment ones. And this would give us the probability of F given C, all right? And then I could do the same thing for negative sentiments. All right, so now we sort of have the mathematics for doing this, and this is our algorithm. So we're going to create an array here. First thing I want to do is I want to sum up the prior probabilities. And so in order to do that, I'm going to go through all the classes, and if the training value is equal to C, this given class, if it has a value of C, then I'm going to place that in this list of rows. And then I'm going to take the number of rows that had that sentiment and divide it by the total number of rows. This gives me PC, which is the probability of that class. And I'm going to do that for each of the classes. For all of the rows, for each of these rows, that's the case with this sentiment, I'm going to find the columns and the data values and make these two calculations. Those two calculations are these calculations, NCF and NC. So I'll sum up these two calculations, and that'll allow me to calculate this. And so now I'm going to go through all the classes and all the features and use these two calculations that I made of this array, using this array and this vector, alpha, and the total number of features to do this calculation. Now, I'd like to calculate the probability of a word given a particular measurement. Okay? And so I've created an algorithm called predict given X. And so first thing we're going to do is we're going to focus on a particular row, right? And a particular row would be a particular set of measurements. And I'm going to pass it my data set, M, and I'm going to pull out of this data set, this is my sparse data set, I'm going to pull out of it the columns that the data exists in and what the data values are. And then I'm going to use this pre-calculated PXC right here. I'm going to use this value to make this calculation. Now this is the sum, this is the way we normally think about it. It's the product of all of, this is how we did the multinomial calculation. This is the probability of measurement X, it's a bunch of series of measurements, given class C is the probability of feature 1 to the X1 times probability of feature 2 to the X2 and so on, given C. But instead of doing this calculation using multiplications, we're going to use logs. Multiplication of larger small numbers, if we take a lot of larger small numbers and multiply them together, we can have numerical problems. For instance, if we multiply a lot of small numbers together, we can result in 0. That wouldn't be helpful. If we multiply a lot of large numbers together, we could reach the dynamic range of our floating point number, and that wouldn't be helpful. Well, so one thing that is often done in this case is to do an equivalent search, equivalent calculation, using logs instead, log algorithms instead. And instead of multiplying these together, we just add the log values. And so this, the equivalent calculation is to calculate the log of p x given c, posterior probability of x given c, is proportional to the sum of x times the log of probability of f given c for all I, f of I. And that's what this calculation does. Now remember that whenever you take the log, this power term becomes a multiply term, and that's what the reason this moved to there. All right, and now we can do our Naïve Bayes calculation. Now remember, a Naïve Bayes calculation was this calculation. Once again, we have the log of this term. This is the log of this term, and so in order to continue to use the logarithms, we're just going to determine the log of the probability of classification C given D, and we'll multiply that times the log of any particular classification times the log of px given c. And this, we're going to do this for all classifications in our set of classes. Well, this would be general, but in our case, there's only two. There's a positive classification and negative classification. All right, now we can do our prediction. And basically all we're going to do in our prediction is we're going to go through all of the rows or all of the movie reviews and call this each time. And then what we want to do is we want to do something called argmax. We're going to take the classification that has the largest value, and that's the classification we're going to keep. So let's say that the classification for a positive sentiment was 0.6. relative likelihood, and the classification for a negative sentiment was 0.5 relative sentiment. So we would say we would make this a 1. It was in this classification, and it wasn't in this one. So we're going to just choose the largest classification, and that's what this does. And this is called the argmax procedure. All right, so let's do a demo now. So we've got the code split up into a library here. And it is, here's the multinomial NB Naïve Bayes, and I added an S to it for my multinomial Naïve Bayes. And then there's just data structures that are set up and available for these algorithms. As we described in the slides, we do a fit, and this supplies data to the algorithm from the CSR, sparse row format. And this does a prediction for each observation. In this case would be a review and a movie review. And this would go through all of the movie reviews and find the best prediction for each movie review and assign it to the prediction that it was the maximum value. So we're going to run this. I'm going to load this algorithm. First thing I'm going to do is I'm going to load in. I brought in a test case, which was a very simple one. And then I brought in the movie database. So for as well, and I could choose either one. So you could just, I highly advise you create a simple test case that you know should work, that is very easy to diagnose, and then switch in the actual test case when you're ready. So these are the stop words, the tokenizer porter as described in the slides. And so here's our movie review data. So I'm going to choose 10,000 movie reviews and plot the, let's see down here. I'm going to bring in this data, this library that I wrote, that we described earlier, and determine the performance. And then we're going to do the same thing with the Sklearn version. And this is the result of that. So we're going to do 10,000 first. And what we see is it uses 6,666 to train, and then 3,333 to test or validate. The results are 94% accuracy from the Sparse Naïve Bayes. From the Sklearn, it was 91% accuracy in training. That's okay. And then 85% accuracy in the Sparse Naïve Bayes for validation. That's good. And 84% for Sklearn. So we got about the same result. Interestingly, though, it took 3.6 seconds to run the Sparse Naïve Bayes, but only 1.4 seconds to run the Sklearn version. Now, of course, Sklearn is written in a C library, and so it's procedural code and is compiled, so it should be faster. So let's do this. Let's go back and rerun this for 20,000. And based on the plot I showed you earlier, we know that at some point the number of as we increase the number of movie reviews, we should see a significant delay due to this dense matrix. Okay, so now we're going to do 20,000, and I already ran this, so here's the 20,000. It's split into 13,333. The results are 85% accuracy in test, and it took 7 seconds, 7.3 seconds. Here's Sklearn, 27 seconds, and had 86% accuracy. Similar results, much faster. And so that was the objective of our algorithm. There are some slight decisions that I made in the algorithm that affect, one or two cases here or there. And since I haven't seen the Sklearn algorithm, I don't know exactly what they did. Thank you for listening. I hope this helps you in something you're doing that you're doing down the road.